Hello, everyone. We appreciate you joining the Stepdad Aviation team today. Over the past few months, our members Chase, Caleb, Jack, Michael, and Surya have been hard at work developing our latest project, the Lifeline aircraft. The ongoing coronavirus pandemic has caused unprecedented damage to lives across the world. However, the advent of COVID vaccines have provided a ray of hope to return to normalcy. Our group has been tasked by the CDC to develop an innovative solution to deliver these vaccines to remote areas. There are many stakeholders who will be depending on the success of our solution. One such stakeholder is Pfizer, the company responsible for manufacturing the vaccine. Pfizer needs us to deliver the vaccine safely within 10 days of receiving them, prior to them expiring. Plus, they must be kept within the original cold storage containers, otherwise, the vaccine contents will fall below the safe temperature zone. Additionally, the residents we'll be serving in Molokai, Hawaii are depending on us the most to deliver them vaccines promptly and following Pfizer guidelines to ensure effectiveness. The US government and the CDC, who assigned us this project, will be depending on us as well in order to accelerate recovery from the pandemic. The greatest risk we've identified is inclement weather, which could damage our aircraft and jeopardize the mission. We will mitigate this risk by ensuring the weather forecast is positive prior to a flight. We also theorized the possibility of radio interference, which severs our link to the aircraft. Our team has implemented a solution to recall the aircraft autonomously if this were to happen. Having identified our stakeholders and risks, we began the design process by considering our requirements. Knowing the distance between our origin and destination to be approximately 76 miles, we then added a round-trip capability with a safety buffer to generate our range requirement of 200 miles. Pfizer requires the vaccines to be held within their cold storage box with dry ice. A full box containing upwards of 5,000 doses weighs about 81 pounds total. During this preliminary phase, our group generated multiple ideas for the aircraft's form factor. The simplest contender was the traditional aircraft form factor, with the propeller located at the front of the aircraft. Another promising concept was a more novel form factor, utilizing a single pusher prop located at the rear. Our final contender was a traditional aircraft with dual engines mounted on the wings.
Ultimately, we had to eliminate the pusher idea since there would be undesirable flow conditions over the prop, causing inefficiency. The dual engine idea was eliminated due to unnecessary weight and maintenance difficulties. Ultimately, the traditional form factor won. We then researched multiple traditional aircraft of a similar weight category to serve as a reference. The pipistrel virus was ultimately chosen as our main reference since it is a light, low payload trainer aircraft. It was the closest analog to our vision. Our group then developed a high-level MATLAB program to estimate the gross takeoff weight of our aircraft based on historical values for coefficients such as specific fuel consumption, lift-to-drag ratio, etc. The code ultimately converged on a value of 995 pounds, which we were able to compare to the pipistrel virus as a reasonable number. Through this weight guess, we were then able to calculate the required surface area of our wing through historical figures for wing loading of general aviation aircraft. Through the surface area, we then formed the dimensions of the wing. Our group elected to have a longer wing in the interest of flight stability. Therefore, our final wing dimensions were as follows. The cross-section will be utilizing a NACA 2415 airfoil, which we settled on since the Virus and the Cessna 172 use a similar profile. This airfoil is desirable for providing high lift at low speed flight, as indicated by the fact that our group calculated a lift-to-drag ratio of approximately 10 for our aircraft. Now that we have some concrete numbers for our design, our group had to pick an engine. To this end, we picked the Rotax 914 engine, which promises a very low fuel consumption and has proven its reliability in countless aircraft such as the MQ-1 Predator drone. Our final set of calculations are as follows. Given a small fuel load of 30 pounds, our aircraft will reach our range target of 200 miles. Additionally, we can maximize our endurance at around 4.45 hours. Putting this all together, we officially present to you our final design for the Lifeline aircraft. Through embarking on this project, we learned how challenging the preliminary design of aerospace systems can be. We also learned about teamwork during a pandemic, utilizing remote working tools effectively to optimize our workflow. Given our current position, our group is ready to move to prototyping and testing of our aircraft prior to deployment. Until then, thank you for attending our presentation.